That's fine enough in the Zoom. So thank you everybody for coming today. This is, as you know, we have a few live talks today and several people are going to be on the Zoom. Everything is recorded and projected, but wonderful to see a lot of familiar faces here, especially having and welcoming to Arizona, Xiangcheng, who is our new theoretical and computational astrophysics fellow at Stewart Observatory. Xiangcheng did his PhD at Caltech, finished in 2018, working with Phil Hopkins. And he works a lot with big computational simulations of cosmological structure formation, and I think Monte Carlo radiative transfer simulations for what happens to protons in the universe. And he has been working a lot with the FIRE collaboration. And since 2018, he was a TAC fellow at the University of California in Berkeley. And I think it was at the time when Elliot Quatert was there, and we were working a lot with him as well. And as of this August, he has been our new fellow for theoretical and computational astrophysics. We're very excited to have him talk to us today about supermassive black holes in the universe and how they can.
Thank you for the introduction. I'm very happy to give this talk. And for people know me better, I work a lot on galaxy formation and the epoch organization and try to understand how those high-ratio galaxies contribute to cosmic ionization and the escape fraction of ionized photon at high redshift. But for today, I decided to change a new topic. And this topic I just started working on not too long ago. So this is also a completely new talk and new structure for me. So feel free to interrupt if I'm not clear on anything. Today I want to talk about supermassive black holes in the early universe and how those supermassive black holes form and grow very massive when the universe is very young. So some historical comments on the supermassive black hole studies. So we know supermassive black holes exist almost in every galaxy that's sufficiently massive in our local universe. The study of supermassive black holes really starts from Seyfert galaxies when Carl Seyfert took the spectrum of galactic nuclei for several galaxies and find very weird features. For example, like some of the emission lines are super broad with several thousand kilometers per second, especially for the hydrogen emission lines. And there are also highly ionized emission lines as well. So this really is, they named this as Seyfert galaxies back in 1943, but this did not caught sufficient attention on this subject until the development of radio astronomy in the 1950s that leads to the discovery of quasars. So the study of quasars begins in the late 1950s and early 1960s, but the landmark of the discovery of quasars is this 3C273 back in 1963. This object first discovered in radio, but later on, when people find the optical counterpart of this object, they find basically a point source, very luminous point source extragalactic. So back then, people named this as quasi-stellar objects or quasars, or QSOs. So for the nature of these type of objects, first people speculate these might be supermassive stars up to 10 to the 8 solar masses. This is one of the speculation back in the early 1960s. I want to mention this because later on, when people think about how these supermassive black holes start to form, these ideas coming back and forth. So this idea of supermassive stars brought up by Oyl and Fowler in 1963, and people realized that these type of objects suffer from GR instability, that for supermassive stars, more massive than million solar masses, that will undergo GR instability and collapse to a black hole. that start from Richard Feynman and Chandrasekhar later on. And then starting in 1964, people start to speculate the power of these sources are supermassive black hole accreting materials, and that released a tremendous amount of energy to power all of these type of objects. So this is very interesting topic, and still people study supermassive black holes until now. So these are some very new, interesting, exciting news in the very recent years. For example, we know our Milky Way had a supermassive black hole at the center of our galaxy, and that first discovered in radio by Jansky in 1931. But later on, the UCLA group monitored the center of our galaxy and measuring the orbit of massive stars around the galaxy center, and find this object is actually a supermassive black hole of 4 million solar masses. And on the right, this is the first image of a black hole. This is actually at the center of an 87 galaxy. This is a massive elliptical galaxies, quiescent galaxy in our local universe. So these are very exciting news in recent years. So just for completeness, we know supermassive black holes exist in almost all galaxies that are sufficiently massive in our local universe. And there's a well-established relationship between the mass of the supermassive black hole and the central part of the stellar component. For example, this is luminosity of the stellar bulk, but this is also applicable to the mass of the stellar bulk. So there's a correlation, a very tight correlation between the mass, black hole mass and the bulk mass. And this is the central stellar velocity dispersion in the stellar bulk. So there's also very tight correlation. The existence of such correlations suggests that there might be some connection, very likely to be some connections between black hole growth and the growth of the central stellar component. Beyond that, we also know now that supermassive black holes are very important in the formation of galaxies as well. So this plot shows this is the classic stellar mass halo mass relation. So the vertical axis here shows the ratio of stellar mass and dark matter halo mass. So if you think all the baryons inside the dark matter halo, that's the universal baryonic fraction, like 16% here. So if you think all that baryons turn into stars inside dark matter halo, this relation should be a constant somewhere around here. But it's not. It has this very interesting shape. Both at the low mass and at the high mass end, the fraction of baryons that actually turn into stars are pretty low. So at the low mass end here, we think this is due to effective stellar feedback that I will touch on a little bit later. And at the massive end, this is due to supermassive black hole feedback, which means the tremendous amount of energy that from the gas accretes on the supermassive black hole actually do a lot of damage back to the galaxy themselves. So this is a slightly outdated picture, but I think still effective. So it shows a major merger of two disk galaxies. And during the major merger, the gravitational torque between these two drive a lot of angular momentum transport that transfer the gas from the disk into the very central region of the galaxy and ignites black hole accretion in both galaxies. And that black hole accretion powers a quasar in this galaxy pair. And that releases a lot of energy, and as you can see, do a lot of damage back to the gas and blow the gas away later entirely. So that leaves red elliptical galaxies with very little to no star formation at all, then quench the star formation inside the system. This is usually called the quasar feedback. On the right, this is show the radio in red and X-ray in blue. This is a galaxy group. If you can see, the scale here is of order of several hundred kiloparsecs, and those relativistic jets from the supermassive black hole inject a lot of energy into the intercluster medium here, and that heat up the gas inside the dark matter halo, and that suppress star formation. By suppress star formation, if you think about the cooling rates from the X-ray, and you work out that into a star formation rate, you will find the expected star formation rate from cooling itself it's much lower. It's much higher than the actual star formation rate inside this galaxy. So basically, there must be some extra energy that balances this cooling. That should be this relativistic jets. So this is the radio feedback. So this is not what I am interested. So for both topics, there have been tons of theoretical developments in the past 20 years or so. I think, although there are many details that still needs to be understood, but the broad picture is more or less correct. So another side of the problem is that why are these supermassive black holes formed in the first place? So here I show two popular ideas about how black holes, how supermassive black holes form as their as the seed black holes. So the left panel here, which usually called the light seeds, those are the remnants of POP3 stars. The POP3 stars are basically formed in the very early universe around redshift 20 to 30 in low mass halos, a halo mass about 10 to 6 solar masses. And that forms stars. The exact initial mass function of POP3 star is still under debate, but usually people think that ranges from a few tens of solar masses to several hundred solar masses. But on average, let's say it's of order 100 solar masses. So these pure model stars undergo pair instability supernova and then explode and left with a stellar mass black hole. So that's of similar masses. So this is one of the idea of light seeds formed from POP3 star remnants. On the red panel here, this is another story. Usually people call them heavy seeds. Those are formed in relatively more massive halo, 10 to 8 solar masses. And somehow magically, if those halos are exposed in Lyman-Warner radiation that can destruct molecular hydrogen, or the formation of such halo is rapid enough such that the turbulent energy dumped onto this into this halo can destroy molecular hydrogen and produce further fragmentation and cooling. Those objects somehow can form a supermassive star of order 10 to the 5 or 10 to the 6 solar masses, and that supermassive star is subject to GR instability and finally collapse directly into a black hole of order 10 to 4 or 10 to 5 solar masses. So this is, people usually call this direct collapse black hole, but actually it undergo this supermassive star and the GR instability phase that form relatively massive black hole seeds compared to the POP3 star remnant story. So the problem, as I said, I work a lot on high-redshift galaxy formation. So the actual problem that drives me interested in the supermassive black holes question is this. So recent discovery discovered that supermassive black holes already exist in the very early universe. So here we're looking at, this is the Quasar bolometric luminosity function. At redshift 6, when the universe is just a little over 1 gigayears old. So this is the bolometric luminosity of quasars. This is the number density of quasars. But there's a one-to-one correspondence of black hole mass and the bolometric luminosity if you think there's some radiative efficiency conversion here. So basically the punchline is that even at this early time, supermassive black holes of 10 to the 9 solar masses or 10 to the 10 solar masses already exist. So how does those monsters come from? This plot is actually very common in the context of high redshift quasar or high redshift supermassive black hole discoveries. I have seen this picture for many, many times that, so basically if you start from a discovered quasar here, you have some black hole mass and redshift of its discovery, you work out picking some accretion model, assuming some radiative efficiency, and you can work out how its growth history is, basically. So in short, you can just pick your favorite black hole seed model, either light seeds from POP3 star remnants and heavy seeds from direct class black holes, and you give it some accreting mechanism or growth history, and then you can feel free to go. So
all of those curves are assuming accretion at the Eddington rate.
Yes, more exactly, it assumes the luminosity is Eddington, and the radiative efficiency is 10% for the alpha disk model. But of course, it can be super Eddington accretion rate just with a lower radiative efficiency. That's also okay. So isn't everything already solved? More or less it is. But this is from the work from cosmological simulations. But this is the blue type simulation from a group of people. This is a very large volume, cosmological volume, is over 400 megaparsecs across. And the mass resolution is of order 10 to the 7 solar masses with spatial resolution in kiloparsecs or so. And they run this simulation to redshift 8, and they can already form a bunch of relatively massive supermassive black holes. For example, for this black holes of order 10 to the 8 solar masses. So there seems to be no problems having those monsters in the early universe. Of course, this is lower than the 10 to the 9 or 10 to the 10 solar masses discovered from observations, but this is a fairly smaller box, and this is also a higher redshift. But if you dig into the assumptions in these simulations, so these are a set of very typical assumptions used in these type of large volume cosmological simulations. So they start from black hole seeds of 10 to the 6 solar masses. This is very massive. And because of this resolution, the dynamics of the black hole is not properly modeled. So people usually use a prescription that can enforce the black hole to stay at the galactic center, at the center of the galactic potential. And they basically assume a Bondi-Hoyle type accretion rate, which is proportional to the black hole mass squared. So if you work out the numbers for this black hole mass and the typical ISM density, ISM gas density at the galactic center, this can, you basically have no problem to make it super Eddington. So this is kind of like cheating somehow, but the problem is that this is super oversimplified assumptions, and actually many other things can go on in these galaxies. So this brings me back to the problem that I work on since grad school, is galaxy formation. So galaxy formation is one of the super complicated and nonlinear problem. So on large scale, it's dominated by gravity and hydrodynamics, and the individual's dark matter halo form in the universe. And within that dark matter halo, gas will eventually cool down and bring the gas toward the center part of the galaxy and form the interstellar medium. So this is the interstellar medium of the galaxy. If you ask where the star formation actually takes place, the star formation takes place in molecular clouds. So individual molecular clouds is only of order 100 of parsecs across. So within the molecular clouds, the stars actually form in protostellar cores. And then after the stars become this main sequence lifetime, then the stars will release a lot of energy back to the molecular cloud. For example, you have photonization from massive stars and radiation pressure onto the dust grains that can disrupt this cloud. And eventually, for the massive stars, it undergo supernova explosion, and supernova explosion deposit a lot of energy and momentum back to the interstellar medium. And that can do a lot of damage to the galaxy. So basically, to study this complicated problem, we're using cosmological simulations. So the blue tide simulation I just mentioned earlier belongs to this category. This is large volume simulations. The large volume simulation usually run a cosmological box of order hundreds of megaparsecs across, but as a trade-off between the box size and the detail of the simulation you can get, the computational power, you cannot use a very high resolution there. So the resolution is usually 10 to the 5 or 10 to the 6 solar masses for baryons and of order kiloparsecs for spatial resolution. Just imagine a kiloparsec inside a galaxy that usually represents a very large chunk of the ISM, but the molecular clouds and other things cannot be properly resolved inside the region. So typically for this type of simulation, you assume some equilibrium ISM states or ISM equation of states, which basically means from this part of from this chunk of the ISM, how much cold gas or how much molecular cloud you expect, and how much star formation you expect to happen based on some empirical scaling relation, and then how much energy you expect that can make it equilibrium. So it cannot resolve a lot of details. But on the right panel here, this is another category that I work a lot on. This is cosmological zoom-in simulations. The zoom-in simulations, we still keep a large box. We just keep the large box to have its the large scale tidal force to make sure we have dark matter halos of the desired mass. So we keep a very low resolution dark matter only box, and we put we increase the resolution and put baryons inside a zoom-in region. The zoom-in region is picked to be around a halo of several times the viewer radii, and that in that sense we can simulate that particular halo with a lot of better resolution. So the resolution we use for the zoom-in simulation is usually of order hundreds to thousands solar masses, and the spatial resolution can be at worst a few to 10 parsecs. But this is much better resolution and details than those large volume simulations. But these two types of simulations are pretty complementary to each other. So the collaboration I came from I joined the FIRE collaboration since grad school. Is the feedback in realistic environment collaboration. That fire simulation used explicitly resolved multi-phase interstellar median and feedback models. So first of all, I want to show this. This shows the formation history of a Milky Way mass galaxy at rest of 0. As you can see, at high redshift, the galaxy formation process is very violent. The gas comes in very rapidly and form a lot of stars inside this galaxy. And the feedback from these stars can explode and blow out the gas entirely from this galaxy. So this is, let's wait a little bit, and now this is the final explosion. And then when gas comes back, it forms a rotationally supported disk, and star formation becomes time steady afterwards. So the interesting observation from the formation history of a Milky Way mass galaxy is that the star formation history actually can be divided into 2 modes. At early times, it undergoes this bursty mode. The bursty mode, which means the star formation rate varies rapidly, dramatically on relatively short time scales. So you see the orange line, this is the star formation rate from the simulations. This shows huge time variability in the star formation rate. And for Milky Way mass galaxy, the transition, there's a transition here around redshift 1 or so. And after that, the gas disk became stabilized inside this galaxy. And after that, the star formation rate becomes roughly constant as the time steady phase, because the feedback self-regulate the star formation inside disk. This is a relatively well-developed theory. So if you think about the star-forming galaxy in this parameter space, so this is the stellar mass, so this is time or redshift. The Milky Way mass galaxy occupies this parameter space. But even though in the early universe around redshift 0, if you go to lower masses, what happens is that galaxies no longer look like the Milky Way mass galaxy, which has a nice rotation supported disk, but more like irregular. So if you measure the star formation, recent star formation history of these dwarf galaxies in the local universe, you also find some strong time variabilities, which indicates the star formation in dwarf galaxies is bursty. Now, if you stay at the same stellar mass but go to higher redshift, this is from the set of fire simulations of massive galaxies at the cosmic noon, led by Robert Feldman, one of our collaborators. So for redshift 2 massive galaxies, there is a broad distribution of morphology. For this galaxy, it looks very irregular and clumpy. Basically, there's no rotation supported structure here. But also, you can find another galaxy that looks like a very nice rotation supported disk. But if you go to even higher redshift, this is the work I've been doing in the past few years, so simulating galaxies at the epoch of ionization. So for the really high redshift galaxies, even at the very massive end, we rarely find that galaxies have rotation supported disk. But basically, all the galaxies are dispersion dominated with super gas rich and turbulent environment in the interstellar medium. So if I draw a line somehow like this, but basically you would expect everything above this line in this parameter space shows bursty star formation with turbulent dominated ISM. And everything below this line that form a nice rotation supported disks. And the transition here is actually the disk settling. Broadly speaking, this is consistent with what observations suggest. So if you look at the fraction of galaxies with rotation supported disk as a function of redshift and stellar mass, basically, although the numbers are still off, but the broad trend is very similar. At a given stellar mass, go to higher redshift, you find decreasing fraction of galaxies have rotations, has rotation, but if you stay at the same redshift, go from massive galaxies to low mass galaxies, you also find a decreasing fraction of galaxies have rotation supported disks. So this, why I want to say a few words about why galaxies show bursty star formation at high redshift. So this is one of the galaxies from my simulations at redshift 5. Now we're looking at a specific starburst episode. I will play the movie on the right. As you can see, at the beginning of the burst, gas comes back to the ISM from the previous burst. The previous burst blow the gas away, and then later on it comes back and form a very gas-rich reservoir in the ISM. Start again. It formed this very gas-rich reservoir, and some of the dense gas starts to form stars. After star formation occurs, supernova kicks in and blow out this kiloparsec scale superbubble. And this superbubble can propagate into the ISM, sweep up the gas, and compress the dense gas nearby. And that can trigger new star formation. So basically, some star formation occurs here and blow out as a supernova, and the supernova remnants sweep up. That can compress the gas nearby and trigger new star formation, and this process just propagate in the galaxy, and eventually everything is blown out. So that's the physics of why we see bursty star formation in high redshift galaxies. As a consequence, so if you look at the stellar image of this galaxy, well, there is somehow very diffuse central component, but as you can see, there is not a very dense stellar cusp in the center of this galaxy. So the potential well is not very deep enough. It's not very deep. And there are a lot of substructures inside this galaxy. Those are individual star clusters. So just remember, for now, the galaxy morphology is very, very clumpy. So this has a very important implication of black hole growth at early times. This is this is the work led by one of our collaborators. I just don't know how to pronounce his name, but he used to be a grad student here. So if you look at, so these are simulations of massive galaxies at cosmic noon. So if you look at the star formation history, this is the orange line here, and the black hole mass growth history, the black hole is actually lagged behind the stellar mass. So the stellar mass grew very rapidly at early time, but the black hole mass did not grow that much. And there's a transition point. During the transition point, the black hole mass shoots up very quickly. And then basically the black hole mass catch up with the stellar mass later on. So this actually coincides with the transition between bursty star formation at early time and the time steady star formation in disks at later times. So if you look at this growth history from this parameter space, so this is the black hole mass versus bulk mass. This implies that the black hole mass did not grow that much until the bulk becomes relatively massive, and then the black hole mass shoots up and catch up. The shaded region here are the local scaling relation between black hole mass and the bulk mass. So in other words, the black hole tends to be undermassive at early times. So we are actually not alone on this finding. There's several other groups also doing simulations with this type of explicit multi-phase interstellar medium and feedback, see similar phenomenon. So I want to say a few words first about the vertical part of this. Like this is the same black hole mass bulk mass relation. So now we're looking at the vertical structure, the vertical part of this curve. If I look at what happens during the transition phase, when the black hole mass actually shoots up really quickly, if I plot the gas morphology during these type of accretion events, I will find this. So this is actually the, you can see very nice rotation supported gas disks. There is actually a well-developed theory about this is if the galaxy has a rotation supported disk and the gravitational torque from major merger or minor merger or even spiral arms or bars that can drive very efficient angular momentum transport of the gas. So the gas will lose a lot of angular momentum and sink to, and flows toward the center of this galaxy. That can gives the black hole a very gas-rich reservoir in the central part of the galaxy, and then the black hole mass can grow significantly during several episodes.
Is there a problem with scale? Those diagrams on the right-hand side are showing regions which are several kiloparsecs across. You can squeeze gas down by these gravitational torques by order of magnitude or something like that, but you've still got many orders of magnitude left to get to the accretion disk.
Yeah, actually, people have done multi-scale zoom-in simulations of this configuration. Basically, from galactic scale, they find gravitational torque bring gas to 100 parsecs, and then people take the central 100 parsecs and re-simulate this thing with much higher resolution and find new gravitational torques, spiral arms or bars from that 100 parsecs, bring the gas to 10 parsecs and pick the 10 parsecs and re-simulate. You can bring gas to 1 parsec, things like that. So next, I want to talk a little bit about the horizontal phase of this diagram. So the takeaway point is during the horizontal phase, there is very little black hole growth in the clumpy galaxies. As I showed you earlier, during the Bursty star formation, the central part of the galaxy is relatively diffuse, and the potential well of the galaxy is not very deep, such that a lot of substructures form inside this galaxy, and there usually lacks a well-defined center. So this work led by one of Phil Hopkins' grad student at Caltech. Of course, we're not related. I'm not related to the first author here, but what he did is doing dynamic friction calculation, throw a lot of seed black holes inside this galaxy and evolve their orbits for a giga year, and see what happens for this black hole seeds. The results are shown in this plot. So this is, let me walk you through this. The y-axis shows the velocity of these test particles at seed black holes. They initially started randomly inside this galaxy of order 100 kilometers per second. And the blue and the red points here shows the final velocity after the 1 giga-year integration of the orbits. If the final velocity becomes next to 0, it means the test particle or the black hole seed sink efficiently at the center of the galaxy. But if the final velocity is much similar, more or less similar to the initial velocity, which means the black hole seed does not sink at all. So basically, the difference really starts at 10 to the 7 solar masses. Only after the black hole becomes relatively very, very massive can the black hole sink to the galactic center in relatively reasonable time scale.
So, I mean, this is just the magnitude of the velocity. Like, I guess, why is this the right metric as opposed to the location of the particle?
Yeah, so actually, just think about it. If the black hole particle is not at the right location, you would expect the black hole particle has a relatively a random velocity.
But this doesn't tell me it's random, it just tells me the magnitude, right? Like couldn't something have an orbital velocity that, in principle, right? Something could have a rapid orbital velocity near the center,
Mhm.
or a relatively low random velocity at the outside of the galaxy, and one of them might have been subject to dynamical friction, and the other one wouldn't.
I think statistically it's
Statistically, sure, but this is a simulation, right? I guess statistically, like if you were looking at real black holes and you didn't have anything other than that snapshot, sure, but why is this I guess it's just confusing why this would be the right metric as opposed to some spatial information to demonstrate that dynamical friction had been effective.
well, actually in the paper both are shown.
Okay,
both
yeah.
the location and the velocity are shown here. So, and I still think statistically there's a similar. You would only expect the black hole particles wandering outside the central part of the galaxy with zero velocity. So this doesn't happen. So another key point here is they basically look at clumpy galaxy versus smooth galaxy. By the smooth galaxy, by the clumpy galaxy, they just took the simulation on where the stars are directly as it is. But for the smooth galaxy, they average the mass in spherical shells. So basically, if you plot the mass versus 3D radius, both models has the same 3D. The 1D profile, but just the mass is average across the entire shell without this clumpiness. So in the clumpy galaxy, the sinking time for these black hole particles becomes 10 times larger. So the picture here you would expect if you have black hole particles wandering around the central part, wandering around this galaxy, it will be scattered by all of these star clusters, GMCs, and things like that. So that makes the sinking problem even harder. So basically, if you think about the black hole seed models, either POP3 star remnant with 100 solar masses, or a direct class black holes with 10⁴, 10⁵ solar masses, none of those models can overcome this barrier. So if you have a direct class black hole in the central part of the halo, and afterwards the galaxy begins to form stars, and there are a lot of things, gas coming in and form GMCs and form star clusters, and the black hole will be kicked around. And that black hole cannot come back to the center, cannot come back to the center of the central part of the halo anymore. So this is a very important puzzle and difficulty for black hole seeds to grow efficiently in high-redshift galaxies. Next, I want to talk about something around the turning point. This is my own work. Basically, think about what happens during this phase and why black hole does not grow until the box becomes sufficiently massive. So here on the right, I will show this movie. This is one of the starbursts of a relatively massive galaxy around redshift 5. This is only the central 1 kiloparsec of this galaxy. The gray here shows the stellar surface density, and magenta shows the gas. So as you see, when gas comes back to the central key KPC of this galaxy, it forms a lot of stars, and as you can see from this image, and also from this stellar density profile, the central part of the stellar density in the central part of the galaxy grow rapidly by order of magnitude. But for this particular object, the black hole does not grow that much. So why does that happen? So I will walk you through this process. So when the gas comes back from the previous burst back to the central part of the galaxy, back to the central part of this galaxy, it fragments and form a bunch of nuclear star clusters. So this plot is only 600 parsecs across, 600 parsecs in radius. So these are star clusters form very close to the central part of the galaxy, but not exactly at the center. And these star clusters orbit around the central part, orbit around the galactic potential, And some of them merge together later on and becomes a more massive cluster and finally spiral in very quickly. And after a few million years, feedback from these newly formed star clusters begin to explode as supernovae, and then clear the gas in the central region of the gas and blow the gas reservoir away. So the entire process happened very rapidly. So if this plot gives a better diagnostics, so if you look at the relative time here, so this is the baronic mass budget within the central 100 parsec. The orange line here shows the stellar mass, subtracted the initial stellar mass, and the blue line here shows the gas mass within the central 100 parsec, and the green curve here is just the SFR integrated over time. As you will see, the stellar mass grow rapidly here. This is only corresponds to the really massive nuclear star clusters sink to the galactic potential and merge there. So the in situ star formation, which can be measured by the green line, that's only a quarter of the entire stellar mass growth. But the stellar mass growth in the very central part of the galaxy, or the nuclear region of the galaxy, dominates by nuclear star cluster migrate toward the galactic center rather than in situ star formation. So if you have a black hole at the center of the galaxy, the black hole does not see much gas coming in. The gas will fragment and form star clusters several hundred parsecs away from the black hole. So that accounts for the disproportionately growth between the stellar nuclei and the black hole. So this is another example, a relatively more massive galaxy at higher redshift. So you will see basically similar things when gas comes back from the last starburst to the central KPC. It forms a bunch of star clusters which eventually merge together, orbit around and merge together to the galactic potential, and then the gas will blow out by stellar feedback. The same diagnosis here. The in situ star formation shown by the gray area only attributes a quarter of the entire stellar mass growth within the 700 parsec. So the majority of the stellar mass growth at the nuclei dominates by these star clusters merging together. So actually, since this process grow the stellar nuclei by a lot of mass, and that increased the mass and the compactness of the stellar bulge. After that process, when gas comes back again from that burst, it will eventually form a rotationally supported disk. And this disk usually, if you watch a little bit longer, it develops a lot of spiral arms and a bar here. That drives a lot of gas inwards and fuse the black hole. But for this part, for this phase, if you plot the same diagnostics, you will see the gas mass is roughly constant. The in situ star formation basically tracks the stellar mass growth within the central 100 parsec. So I want to talk about the physics, why since you have a very compact stellar nuclei, you have a compact and massive stellar nuclei or super compact bulge, you would expect this can stabilize. Why that happens? So that for this time, I run idealized controlled numerical experiment. I set up an isolated halo of 10 to 12 solar masses, basically around redshift 8, and I manually add a spherical bulge component. For both movies, the bulge mass is the same, but I use very different scale length. So this one is a super compact bulge, but this one is relatively diffuse. And the gas distribution is taken from cosmological simulations and are identical between these two experiments. So basically, you think I have dark matter halo and I have a spherical bulge at the center, but with different scale length, and I start to pure gas onto this system. And what happens later? What happens is that, as you can see this, for this one, the bulge is not that compact, so the potential well is not deep enough, and you can see star formation begins not at the center, but several hundred parsecs away from the center. If I replay this movie, for this configuration, star formation begins not at the galactic center, but several hundred parsecs away. There are a bunch of star forming regions, and each star forming region form a bunch of star clusters, and those star clusters begin supernova blow off as a supernova explosion, and then disrupt the process. But for the right configuration, this is a super compact bulge. When gas comes in, it does not form star until the gas reaches the center and build up this reservoir, and you form a rotation supported disk. But basically, the physics is that if the bulge is compact enough, the tidal force, which is measured by proportional to mass divided by radius to the third, that can prevent gas fragmentation, and that can allow the gas to come to the center and adjust themselves into a rotation supported disk. And then star formation can happen inside the disk. And there are also structures in the disk that can bring efficient angular momentum transport from the gas towards the center, until the black hole grows. So basically, this is just a summary of what I just said. If you have the same bulge mass, but with a decreasing scale length, that means the bulge is more compact, you would expect to form a rotation supported disk. And if you keep the bulge the same scale length, but increase the bulge mass, and you also expect to have a rotation supported disk if the bulge is sufficiently massive. So the parameter combination is actually the key here that prevents the gas fragmentation and allow the gas come to the center and form the disk. And finally, just to put everything together, I just said, during this galaxy formation or starburst episode, several nuclear star formation formed in the central 100 parsecs of the galaxy. And these nuclear star clusters merge together, and they are guaranteed to sink to the galactic potential because these nuclear star clusters are fairly massive. And then as the stellar nuclei becomes sufficiently massive, and because they're very compact, you would expect to stabilize a gaseous disk. And since the gaseous disk form that angular momentum transport from spiral arms or bars or mergers will bring a lot of gas inwards that fuels black hole growth. So why I like this picture a lot is because these runaway stellar mergers inside the nuclear star clusters may form relatively massive black hole seeds as well. So if you think about the POP3 remnant or the rock collapse black holes that I told you earlier at seed models, those are usually form isolated black hole seeds. But for this is black hole seed embedded in a very massive star cluster. And those type of configuration are guaranteed to sink to the galactic potential and not wandering around on reasonable timescales. And the other bonus is that so nuclear star clusters are relatively massive, but the relatively lower mass counterpart of nuclear star clusters are globular clusters. In globular clusters, there's a very interesting phenomenon that has not been understood yet, is that there are multiple populations where there's some abundance anomalies, usually in this helium, CNO and sulfur or sodium or aluminum, these type of elements. People speculate whether these are come from a second generation of star formation in globular clusters, or another popular theory about this abundance anomalies is form supermassive stars by runaway collision of massive stars in globular clusters that undergo a supermassive star phase can generate a lot of these heavy elements that can pollute the globular cluster. And another interesting side of this story is that we have some observational evidence connecting nuclear star clusters and supermassive black holes in the local universe. So I really think if this is a more elegant picture that can tie a different problems all together into a more coherent with less fine tuning, that this could be the final answer of this problem, I hope. So I think I'm getting close to the end of the talk. I'm happy to stop here and take questions.
So this is a very basic question, but I recognize the basic physics you laid out makes a lot of sense, of the reasons why you would have slow growth early on and then rapid growth later on. But how do you reconcile that with very ancient, very massive, supermassive black holes? It seems like you described the solution, but not to the problem that I thought the observations were telling about.
I'm sorry, I didn't really catch that. What do you mean by?
So I guess maybe this is where maybe I just don't understand the observations well enough. My impression was that one of the most surprising observations was very high redshift, very massive black holes that seem to have grown too quickly. What I think I understood here was that you explained why, say, Bondi-Hoyle accretion overestimates growth at early times and underestimates growth at late times. But it doesn't seem like that would solve the problem of explaining the most massive, youngest supermassive black holes. Yeah,
so actually the problem I try to outline is that observations find these really, really massive black holes in the early universe, but those are very rare. So if you look at the large volume cosmological simulations, they have no problems reproducing those populations. Using Bondi-Hoyle type of accretion, very, very massive seeds. They can reproduce that. But the problem that I'm trying to outline here is that they oversimplify this problem, and that should be extremely difficult.
Right. So I guess, so you're saying naive simulations overestimate, like the physics they put in overestimate early black hole growth and nevertheless reproduce observations. You've shown why those simulations should be incorrect, but that doesn't necessarily resolve the problem that we still see the supermassive black holes at very high redshift in the universe, the real universe.
Yes. The problem is that in our type of zoom-in simulations, we also have very massive galaxies at every time, and they can actually stabilize as a disk. So we speculate if they stabilize as a gaseous disk, and then the black hole can catch up very quickly, and that leads to a supermassive black hole.
Okay, so the time scale on which the very most massive galaxies in your zoom-in simulations catch up is sufficiently early to explain the observations.
Yes.
Okay, that was what I missed. Okay.
Yeah, the only difference is that for the large volume simulations, they produce a lot of black holes of 10 to 7, 10 to 8 solar masses, but we would predict they don't exist.
Right, but we don't have observations to suggest that they do, so that's okay.
Yeah.
Okay, thanks, that helps a lot.
If I might follow up on that, if we were to make an observational and signal relation of, let's say, 5, you predict that it will not be as correlated. Because you would have the massive galaxies that are stabilized at the high end will be there, but at the low end, there will be an enormous range of all of those that are trying to catch up.
Yeah, so I think there will be a transition point when the when gas stabilize and the black hole catch up, there's well established and sigma relation. Below that, it should be a huge scatter.
Is there any possibility of doing an M-sigma relation not relative to 5%?
I guess not.
Yeah.
With JWST?
No, it's the key point is how to measure the stellar velocity dispersion in the central part of the galaxy. It's basically impossible.
You can get the luminosity of the bulbs, but nothing more than that.
Could you do it statistically? Like just with, if you just had like black hole mass estimates at high enough redshift, you could make a statistical argument that they should look different if they followed the M-sigma relationship or not, based on the mass function?
My impression is that observationally, this is even very difficult at lower redshift, redshift 1, 2. The key point is how to remove the contamination, have the signal you want.
More questions? I don't know how we do the remote
You
thing.
can check and see if somebody's put them in the, you can ask people to put it in the chat.
Do you want to ask if anybody on the Zoom has a question?
No, I don't see it.
I didn't see any either. Yeah. I think on that note, let's thank our speaker one more time.
Yeah, how are you?
I'm good, how are you?
Okay.